Today we're going to talk about present value annuities. So we'll start with our definition. Annuities can also describe an account from which a person receives equal periodic payments or withdrawals. That is, if you invest a lump sum today, so that at regular intervals you'll receive a fixed sum of money. The single sum of the money required to purchase this type of annuity is called the present value of the annuity. So this is kind of like paying for a retirement package. So you work all your life and you're so used to getting a paycheck every month or every other month or every week or every other week. And so you take a big lump sum of money where you can start taking equal payments that are kind of like your paycheck except you're not working, so that you don't have to change dramatically the way that you're living because you're getting essentially the same amount of money you were as your paycheck except now you're not working. So here's the formula for a present value of an ordinary annuity. A sub n, this is actually one variable by itself, equals r times the quantity 1 minus 1 plus I to the negative n, so you have to give a negative sign here, all over I. A sub n is the present value. That's the big lump sum of money that you stick into the account that you continually withdraw from until it runs dry. R is the continual withdrawals. That's how much you get every month, every other month, every week, every other week, however you have it set up. I is the interest rate per period, found by R over M, where R is the interest rate and M is the number of compounds. And N is the number of investment periods, found by N equals M times T. M is still the number of compounds, and T is time, usually in years. So for example, let's find the lump sum needed to invest into an annuity so that we can get $1,000 at the end of each month for the next 16 years. The annuity pays 9% compounded monthly. So we'll first start by finding all the components that we need for our formula. R is the continued withdrawals. We're going to withdraw $1,000. I equals R over M. So we get our 9% turned into a decimal divided by M, the number of compounds, monthly would be 12. And N equals M times T, 12 times we're doing this for 16 years. Now that we have each of these components, we can plug it into our formula. Now we want to take our time, again, like before, doing these calculations. Do any basic simplifications first, add these two numbers together, and now we want to simplify this numerator. I'm going to take the 1.0075 and raise it to the negative 192nd power first, and now I'll take 1 and subtract that number. Like we've talked about previously, save your rounding for the very end. Write out your very long decimals. When you subtract those two values, you get 0.76179576664. Divide that by 0.0075. And now we can multiply that 1,000 in. And we get 101,572.7689. So that's the amount of money, that is the lump sum that we need to invest today so that at the end of each month for the next 16 years we can withdraw $1,000. So if you recall from previous lessons, annuities due is the one where the payments are made at the beginning of each period. So again, that keyword beginning. This means you're going to get that one extra interest payment. So it's the same formula as an ordinary annuity, but the annuity due has this extra 1 plus I at the end multiplied in for that extra interest payment. All the variables have the same meaning as an ordinary annuity. This is the lump sum you need to withdraw from. These are your continual equal withdrawals. I is R over M, interest rate over number of compounds. N is M times T, number of compounds times time. So for example, let's say we won the lottery. If you win the lottery of $1.2 million, that's awarded in payments of $10,000 at the beginning of each month for the next 10 years. So congratulations, you're getting $10,000 at the beginning of the month for the next 10 years. Now, the lottery found an account that they could invest money in that would give them 7.8% compounded monthly. What is the real value of the prize? So the lottery isn't going to stick $1.2 million in this account. It's going to stick a lower sum, and then based on the interest it makes, it'll make these equal payments to you for $10,000 for the next 10 years. So what we're actually looking for is the amount of money that the lottery needs to invest in this account today. So let's break it down into its components. R, the continual withdrawals, that's the $10,000 you're getting every month at the beginning of the month. I is R over M. That's 7.8% divided by, you're getting monthly payments, 12. And N equals M times T, the 12 payments that you get for the 10 years, or you get 120 payments total. So now when we plug this all in, remember beginning means it's an annuity due, so we need that 1 plus I at the end. Now we just have to slowly go through our calculations. Do all your basic simplifications first, the 1 plus 0.0065 here and here. Now, just like we did before, I'll take this 1.0065 and raise it to the negative 120th power, and then subtract that from 1. Take these two numbers and divide them. And now I have 10,000 times the 83.14391987 times 1.0065. Multiply that all out together, and it turns out that the real value of the prize is only $836,843.55. That means the lottery only has to put in that $836,000 into this account to pay you those $10,000 every month for the next 12 years, or 10 years, sorry. But the rest of that $1.2 million that you earned for your prize, that comes from the interest that they earned from this account. So that's what a present value annuity is. The big difference between a future value annuity and a present value annuity, a future value annuity is when you're putting money in and the account grows. A present value annuity is when you start with a big chunk of money and you withdraw from it until the money dwindles down to nothing. Okay, see you next time.